Anyway, so I'm Nolan Ramsler. I run a local company called Mapper, also known as Co-Productions. We hack other people's cameras, and we have our own cameras for drones. So we cover a full gamut of most of the smaller cameras. So when GoPro was doing more business, we were the world's largest GoPro modifying company. So we would hack it, we'd take their lenses out, put non-fisheye lenses in there. We still do that, but of course at a lower capacity. Mapper is a sub-brand where it's kind of our cameras. Our kernel cameras are a new camera we're launching this summer/this year. It's basically a modular custom camera. You can build your own arrays, so you can choose your sensors, your filters, your lenses. It's open source software, open source CAD design. You can build your own arrays. It's designed for drone OEM manufacturers and people that want to integrate the product to their own requirements. Software is open, that kind of stuff. Not a pitch here, just who I am, and I've been hacking cameras for many, many years and learning as much as I can about it too. So I started from nothing, and I do not have a degree in cameras, but I've been in and around my whole life. Okay, so typically when you think of surveying from an aerial perspective, you have two different types of cams. You have the color, the RGB guys that are either collecting RGB imagery or they're looking for information like surface models for 3D modeling, stockpile measurements, topographic maps, DSM, all the sort of elevation, terrain information. RGB imaging, of course, you can do site survey and construction. The other side of the thing that we do a lot of with our customers is multi-spectral data, and that allows you to check on vegetation, either species delineation, which is the ability to say, okay, there's this species here, there's this species here, or we do conservation, environmental stuff a lot, where we look at, we build a camera array. That's the advantage of having a modular camera system, that you can build an array for a specific species detection. You say, I want to just look at sagebrush. Then you basically go out to the field or look up and research the particular spectral signature that those particular plants are reflecting. You take that information, you build yourself a custom economically priced array, and then you go out and fly with that. You got another project, you swap filters, you then go fly with the same camera, just different filters. So that's a lot of what we do, is the vegetation analysis. So I'm going to dumb this down a little bit in terms of cameras, because this is about sensors. So I got to start with pixels. Obviously, most of you know probably more pixels typically means higher resolution, but it also means lower ground GSD, ground sample distance. And GSD is going to be the main thing that if you're looking for a camera system and you're doing surveying, you want to know what kind of resolution you're looking at, depending on if you're looking at RGB, so color imagery, versus multispectral. Color imagery, RGB imagery capture is much more important to have more pixels. Multispectral imagery is not as important, but it's still useful. Never to have too much information. Up to the point where a larger megapixel system is going to create larger file sizes, which require larger uploads and processing. You saw drone deploy. Cloud processing, which I will touch on at the very end of this, is useful, but there are limitations in terms of data connections, project image sizes, so there's certain limitations that you have to keep in mind. So sometimes you don't want the highest resolution. And the other factor is that larger pixels, which you typically get on the larger sensors, have better low light performance, which if you're outside, doesn't really matter at some point. But it also captures less image noise, and that's important when you're thinking about infrared light. We'll get into that in a minute too. But price, as you can see kind of where we're at now in the industry, a 100 megapixel camera is actually now down to a very reasonable size, but the price is still up at $17,000. Most of you know the Phantom 4 Pro, 20 megapixels for only $1,500. So talking about the curved camera arrays, this is an example, a mock-up of our kernel camera. So essentially getting 6 14 megapixel cameras together into a curved color RGB array essentially will give you a 75 megapixel single shot image for about $10K. So definitely a price difference to a single sensor system. So we've designed kernel to not only do multiple sensor types like multispectral versus color, but the curved camera arrays is something that a lot of our partners are really interested in. It's basically bringing down costs on the higher resolution sensor arrays. And the ability of this, because it is curved, essentially if you think of the field of view of all the lenses, they all go to a common aperture, common point in space. And essentially, once you calibrate the camera array, it becomes a camera. So you've taken 6 cameras and you form a camera. And so that single camera can now shoot a high resolution image that's also depth, and it's got 3D depth to it, like photogrammetry, like you saw with the drone deploy stuff, and it also is measurable. So once you completely characterize a curved camera array, and you know the exact orientation of the sensors and everything, you can actually take a single shot and you can measure it. You don't need to do a full photogrammetry, multiple sensor array kind of situation. So curved camera arrays are really kind of where the industry is going. You'll see, if you have a newer iPhone, you have 2 sensors on there, most of you, if you have that phone. So a wide angle and a medium and a narrow angle. That is also kind of where the systems are going. So if you're in the production scene at all, and you've seen the Hydra system that they hang this is kind of modeled after Shotover's Hydra system. It's a giant 6 red cameras that they put together into an array very similar to this, and they use it for super high resolution photography for the backdrops for movies. So there's many different industries. We have customers that want to combine this kind of imagery, capture with LiDAR systems to either supplement and or replace some LiDAR systems because of a huge, measurable, high density resolution image. You can supplement a lot of LiDAR systems in any report.
So you're able to save everything in RAW and JPEG and GIF formats?
It's all, yeah, you can do RAW too. So getting into different sensor shutter types, global shutter is still, in terms of surveying, is still the best. Mechanical shutter is essentially blinds of sorts. People think of it as the old school way of doing things, but it's still used. Mechanical shutter basically goes over an electronic shutter sensor, and if you're familiar with the Phantom 4 Pro, what they use is a combination. They have a rolling, so in case you're curious, there's no 20 megapixel sensor that's global shutter that exists. So first off, the global shutters are very low volume, low production, very expensive, and very low resolution, but they're getting more and more high resolution as more stuff is being manufactured. So what a lot of customers, or what a lot of companies, like say DJI for instance, who wants to put a 20 megapixel camera on a little tiny drone, there is no global shutter sensor that's 1 inch, it's 10 megapixel, that's the max, at that 1 inch size. So they did a rolling shutter with a mechanical shutter over it. So if you've looked at their specs and you're wondering why the shutter speeds only go to a certain max 1/2000th of a second, it's because the mechanical shutter has only a certain speed that it can go over the sensor. And after that, you then have to go to the electronic shutter to basically capture the information. So the differences between the global shutter is what this global shutter is doing. It's basically saying, okay, boom, let's capture all the information. Mechanical shutter is a mechanical system where it comes down and basically captures everything, then closes it off, and opens it back up. So it's essentially the same thing as a global shutter, but it's a physical moving part. So with drones, there's a limitation in that high vibration environments and life of a mechanical shutter. I don't know why DJI didn't post it, but there's some sort of life involved with how many photos you can take with a mechanical shutter. It's 100,000 or 200,000. Maybe they assume people won't be doing it.
Before it wears out.
Yeah, before it wears out, it needs to be replaced. If you've ever gotten any big digital SLR or medium format or full frame, those camera manufacturers, Canon, Nikon, those guys, they will list a typical mechanical shutter life, and then you can send it in and get it replaced and that kind of stuff. So mechanical shutters are great. They're very useful if there's not a global shutter of the megapixels that you want to use. Rolling shutter, you all know about those. They're in all of your cell phones. They're in every GoPro and small image sensor, basically of any sort of resolution. They do have issues though with image flow. Your question, sir?
Yeah, this may be a dumb question, but I've always been curious, why does the CCD even need a shutter? Why can't it say, I'm going to have a certain exposure time, at this time I'm going to start counting photons,
Yep.
and then I'm going to stop counting?
That's a global shutter. The problem is that in order to collect all that information fast enough, like think of video.
Yeah.
So 30 frames per second.
Right.
That image processor, the thing that's reading that pixel information has to be fast enough to read every single pixel within that tiny little exposure moment, save it, get ready for the next picture, 30, 60 frames per second. So it's very, very tough for them to be able to do that. And then the sensor manufacturers also only make, sensor manufacturers make X amount of this kind of product and X amount of this kind of product, and the costs are involved with that. So global shutter, there hasn't been, the industry that's driving global shutter is the machine vision. Basically web camera scanning of packages or medicine bottles or basically machine vision in shipping and stuff, and they haven't needed high resolution because they just put narrow lenses on and get into where they need to see. If they want to see a little tiny barcode on something, they just zoom in right into it and then they can see it. So they're more concerned about noise, image noise, low light performance, that kind of stuff. So global shutters, you'll typically see all these other capabilities and all these other benefits, but not resolution, because it's not as needed as much. But yeah, why isn't everything global? Great question. I don't know. It's basically Sony and E2V or whatever the other companies are that are driving the global shutter high resolution stuff. So.
Isn't there a discharge time also on the CMOS sensor?
Yeah, a lot of ability to read it, there's lots of different stuff. And I don't even know too much of the technicality down to the really, really low levels. So, lots of anyway, sorry, rolling shutter. If you ever, this is a photo of one of our customers decided to strap a camera to something that obviously is vibrating like crazy. So a rolling shutter is scanning from the top to the bottom, and you may not be able to see it, but every propeller-based platform vibrates to some degree. And so every oscillation, even as small as it is, will cause the camera itself to move. So if it's coming down and saving the information from the top to bottom, it's going to save it as it wiggles down. And that produces effects that probably aren't realistic, maybe in some countries, I don't know, roofs curve like that, I don't know. But essentially this is not good for stitching, for photogrammetry. Not obviously past the issue with it not representing what you're actually trying to shoot, but it also is difficult to do tie points in your stitching software. So a lot of times, if you do have this information, you need to balance your props, please, which is one of the biggest things with the toys, like lower economical platforms. Nobody balances their props. It's like, hello, vibration. But most of the gimbals these days, for the cameras built onto the drones, do not have this issue because they've tuned them so well. It's more for a lot of our customers that want to strap our little survey cameras to what drone or whatever, and they don't properly isolate it from the vibrations of the motors, so then the vibrations get to it. So a couple other things about shutters real quick. Again, we talked about global shutters. So the mostly lower megapixel, the 1-inch size sensor that's on the Phantom 4 Pro, for instance, the max global shutter that exists right now in the world, is a 10 megapixel. And then, so that's a 1-inch sensor, a 2/3 inch sensor, the max is a 5 megapixel, and in the lens size that's in, say, a GoPro or a DJI X3 camera or a Phantom 4 or Phantom 3, those max out at 3.2 megapixel global shutter. So just to give you an idea. So if you wanted to have, say, a Phantom 4 with a global shutter, it would be 3.2 megapixel. Just to give you an idea of resolution. So some of the issues with mechanical shutter we already talked about, high vibrations, and shutter has a life, max life. Rolling shutter, as again I said, it's fueled by the cell phone market, and so there's lots and lots of tiny, high resolution. I remember, I think Sony definitely has a 23 megapixel. That's the same size as a GoPro sensor, which I think the newest iPhone has the same size sensor, but again, it's lower resolution. So it's the cell phone market and any of these markets like CCTV industry has fueled rolling shutter because for the majority of them, you can mitigate the issues of rolling shutter if you're not vibrating, which if you're on a cell phone, really not an issue unless you're moving all over. So you can reduce your exposure settings, and I believe they probably take some of the accelerometer into account to possibly reduce that as well. And then if you do have low vibration, a fast shutter speed will also greatly reduce these issues, and you can essentially get the same quality as a global shutter. So for instance, on our curved camera arrays, like I was talking about, we're using 14 megapixel sensors. There is no 14 megapixel global shutter sensor, so we're using rolling shutter, and what we're doing is a bunch of tricks, but one of them is making sure that the exposure settings and the vibrations are greatly reduced to nothing as if we can on well-balanced gimbals and isolated dampening ball mounts. But the other thing is making sure that the exposure settings don't show that rolling shutter. There's other things, tricks we're doing too. So as a general overview to geotagging images, this is less of an issue now than it was a few years ago with aero-based imagery. Most cameras now either have a really low quality. Most cameras that are separate from a drone have typically a GPS chip built in, but typically the accuracy on that is not very good. So also similar to DJI products, they have cameras on them that have built-in GPS, so the GPS from the drone is actually being used to tag the images, so all the images have that GPS information embedded. So that's the one side. The other way that a lot of people have done over the years is if your camera doesn't have GPS built in, like for instance back in the day with GoPro customers, that use the flight log of the drone. So the drone is tracking all the information during its flight, and you're matching the timestamps from the flight log to the timestamps of the cameras, and you're matching that up to say, okay, this is a GPS point at this particular picture. That's kind of the two ways of doing it. Obviously, if it happens automatically, that's the best way to do it. There are issues, though, in the accuracy of the GPS. So using DJI as another example, even though they have a new MT200, MT210 matrice platform with RTK as an option, the RTK is only able to be used for position. It's not used for really for geotagging the information of the exposure of the images and getting that accuracy to a point where the photogrammetry accuracy to get survey-grade aerial surveys can be basically realized. So there are two technologies that are used, and I'm sure DJI will come out with it, but the other companies that are doing geotagging are using RTK and PPK information if you're trying to do real-time or non-ground control point-based corrections to your 3D model, 3D work. So RTK and PPK are kind of buzzwords. RTK is basically you have your ground station and you have the drone, and the ground station is receiving a constant stream of high accuracy GPS information about where it is fixed in space, and the drone also has its own GPS information as it's flying around, and they are communicating back and forth to create and continuously correcting each other to improve the accuracy of the GPS on the drone. And then that information, depending on your payload system, your camera company that you're using, can either use that information automatically from the drone's GPS and tag images with that as the exposure moment happens. If the camera does not support automatic emitted GPS geotagging, then you'll have to do the PPK process, which is essentially recording that log file, not necessarily using the drone one, but a lot of companies have come out with third-party tools where they are recording, they're connecting to a GPS either on the drone or externally, another GPS antenna, and they are recording a very, very high-quality GPS track, and then you're again matching that time to the camera time and matching and correcting that, and reducing that. So these are just some examples. Pixhawk has the ability to receive the exposure signal from a camera system if it supports it, and that exposure signal pulse on the PWM pins can be used to know better about when that particular camera fired, and that information doing they don't really call it PPK, but it's essentially PPK. Basically, they look for that log line in the log track, and then use that to improve and or apply the GPS position to the camera images. Siegel, basically, they have something that called a MapX that records the data to a micro SD card. And DroneBit, this is their version 2 they just launched yesterday. This is their PPK system that they've been selling quite a few of. So a lot of people talk about GPS accuracy in your results. You always have to think about where you want to finish, like what the product you need to deliver is, and work backwards. You want to figure out what inaccuracies exist and how you can try to mitigate those either during capture or in post. And a lot of it is you've got to use ground control points for most of this to properly locate your orthomosaic if you're interested about having it aligned in geospatial in the GPS space. If you're more concerned about the accuracy within, or if you're concerned about the accuracy within your captured information, you're looking for horizontal versus vertical inaccuracies, and those can obviously be improved with ground control points, but having each image properly geotagged is also very, very important. So these technologies are going to become kind of in the background as we move forward with the drone space, because the drones are just going to do them automatically. Like our kernel camera, for instance, is reading the UAV CAN stream, which is a new data stream coming from the Pixhawk-based systems, which is the same 400 Hz data stream. And and we're reading that as a constant stream right into the entire camera array. And as soon as we are in the exposure moment, we're grabbing that information directly and sucking that and putting it onto every single image.
So you use it like timestamp.
Yeah, we're using it down. We can actually get it down to nanosecond accuracy. Yeah, it's we like to say millisecond, but it's obviously nanosecond is part of the millisecond. So it's really accurate. The camera takes an exposure. We've got the stream, and it's like, okay, when do we grab that stream? And it's like boom, right there. And so we're kind of doing, and we can use RTK GPS systems in that. So we're doing PPK on board and with the compatibility of RTK systems. So that's kind of where a lot of, I think, camera manufacturers are going to be going if the drone isn't already going to be doing it themselves. Basically, sensitivity of sensors, thinking about light and what can you do with different wavelengths of light, and what industries are, what different industries can do with it. And so we're going to start from the general sense and delve into it. So sunlight basically covers your visible light that your eyes see, and the entire infrared spectrum. The entire infrared spectrum can be broken down into near, mid, and far infrared, also called shortwave, midwave, and long wave. And far infrared is also commonly called thermal. As you know, our eyes see basically from deep blues to deep reds. So it's roughly 400 to 700 nanometers. And a sensor that typically is used on our cell phones, the RGB camera sensor, the CMOS, it's typically CMOS, and it's typically built with silicon, and that sensitivity range is about 400 to 1100. So even though the visible spectrum for color for our eyes to see is only 400 to about 700, the sensors we're using can actually see beyond that up to 1100. So this is where multispectral cameras kind of have some prevalence, is that we use black and white monochrome sensors like this standard CMOS curve you see here. And so you're going to see a bunch of these curves here in the next few slides. The bottom row is the wavelength, basically the wave of light, and the left side is going to be the percentage of either transmission or sensitivity, or basically the amount of light that particular sensor can capture those wavelengths. So you can see a CMOS silicon sensor can capture visible, and then you can also capture near infrared. And the values range from 400 to 1100, which is 0.4 to 1.4 micrometers. You get into the FLIR sensors, like the thermal far infrared sensors. This is a spectral curve for an example for some of the FLIR sensors. You can see at the bottom, instead of 0.4 or 1.1, we're going 6.5 to 14.5. So 6,500 nanometers to 14,500 nanometers. So the big difference between the visible light that we look at and the thermal imagery that's far infrared has to do a lot with the inverse relationship between temperature and wavelength. When we're using a visible light camera in near infrared, we are basically looking at a light source's reflected light. So the light that we're capturing, the photons of light that we're capturing into the sensor as information is essentially being produced by a source separate than the subject matter typically that we're looking at. So for instance, the sun is bouncing light off the ground, and we are capturing it from the ground. That is reflected light that we are capturing. Far thermal infrared is emitted light. So we are not looking at light bouncing off of it to the subject matter. So if you had a person standing there, we are not looking at the light bouncing off of them to capture them. We are capturing the light coming off of the person. So there's an inverse proportion. So as you go higher in wavelength, you're able to detect temperature. And as you go lower in wavelength, you can still detect the temperature, but it has to be like the temperature of like the sun. So, right, you got really high, low wavelength, really high temperature, or long wavelength, really low temperature. So plants also, just like any other object, reflect light. And the difference with plants is that different plants obviously are different colors, or different plants reflect different wavelengths of light, like infrared. So NIR, this is a very common graph to explain photosynthesis, and basically when photosynthesis is happening, a healthy plant is reflecting a lot more infrared light, and an unhealthy plant would be reflecting less light in the infrared spectrum. As you can see in the visible spectrum, it's very, very close. They're within percentages of each other in terms of how much light they're reflecting. So, when we see a dead plant, when it's brown, it's obviously dead. But we can look at green plants and actually see a difference in health before our eyes can detect it. And that's what multispectral imagery and seeing that near-infrared spectrum and beyond is really important for capturing information from vegetation. And of course, soil or any surface, asphalt, water, they all have different spectral signatures. Soil is, as you can see, very flat, and so even less reflective in the infrared than the unhealthy plants. Extending this graph even further, we were just looking, the graph we were looking at was just the left half of this. The NIR plateau that we were just looking at is also labeled there. But if you had a camera that was sensitive past 1100, so outside of the silicon CMOS sensors, one that was capable of looking at shortwave, you would see these other three water absorption troughs for plants. And so water absorption is something that a lot of the thermal imagery customers are looking to try to use. But the biggest issue is that you need shortwave IR, and it's really expensive, and really big and heavy, and it's not there yet. It's probably where thermal was 40 years ago or something. It's going to take some time probably, and I think there are some companies coming out with it, but until a real good shortwave system for a lower cost comes out, it's not going to be as widespread. So for now, we typically deal with the work within the 1100 and less, and we work with those peaks and troughs there to get information. It's the red edge that you may have heard. That's another term, red edge, and that is what that refers to. Is red light is down in the troughs here in the red spectrum, and the NIR plateau is up here, and the red edge is between NIR and red, and that's essentially this very, very quick, as you can see, steep drop in reflectivity where we can start to really quickly detect if the plant's starting to get unhealthy. And so, yes, we can detect it based on just the NIR light here, but when we start to measure one thing and it starts dropping like crazy, we know that it's going down to death.
How does this technology or this translate to not just healthy versus unhealthy, but one type of plant versus another type?
So that gets into just the spectral signature of a plant. So most...
If they're similar, you're out of luck.
Depends on how similar.
Okay.
So to get that information, you need to use what's called a ground spectrometer, a field spectrometer, or a hyperspectral camera. So hyperspectral cameras essentially see lots and lots and lots of narrow bands of light over, they basically build this three-dimensional cube of information that captures an image at very, very sliver nanometers and scans the entire spectrum. And they're very expensive and they're very expensive, they're coming down in cost, they were very big, they're coming down in size. And so eventually multispectral probably won't be as useful, but it'll be even cheaper than hyperspectral. So hyperspectral systems and ground spectrometers measure a particular scene in front of them's spectral signature. So when we have a ground spectrometer in our office, we can take it, point at a red object, and we'll see some information, but at red we'll have a huge spike. Or a particular plant, we can point it at it, probably take like 10 or 20 of them, and say, okay, plant, you are this particular spectral signature. This is something found near you. Okay, we want to know when we see you, we don't see you, so we need to take your spectral reading and your spectral reading and then take that data. And this is where a lot of the newer AI and machine learning information for reading hyperspectral data is coming from. The reason is because they want to do species delineation and try to do that without getting into Excel like we do it right now, or GIS software, and try and find that particular spectral contrast. We'll get into contrast here in a minute, but yeah, it's a very good question. That's where this industry is kind of going, and the way...
It hasn't arrived yet, it's on...
It has, so the problem is having a camera system that is adaptable to your particular project, and I don't want to push my own products, but that's why we designed Chrome to be completely customizable, to swap sensors, to swap filters. So you take a hyperspectral or ground spectrometer and you image your plants, and then you can determine what spectral signature array you need to build for a much less cost than, say, trucking around a hyperspectral sensor. And then you take this little tiny sensor array and you use that's specifically tuned to that particular project, and then you go do your surveying and stuff. And then you bring in GIS and you do all your contrasts, and that's how you get your results. You got another project, you find that thing, you swap filters, you go do that. So there's not a lot of camera manufacturers doing it because
the cost is switching up filters if you have
Filters are
specific
$60,
projects that you want customized. So it's
Yeah, there's not a lot of most camera manufacturers are doing very similar to things like DJI. They want to sell you one system, and you might get swappable whole camera payloads, but no customization, no
a
modifications.
one size fits all.
So, anyway, that's a business marketing conversation. We can talk later about that if you want. Okay, real quick. So, getting back to reflected versus emitted. This is a Orange Grove, near the Wild Animal Park. And so this is basically a mono camera with a very narrow band 808 nanometer filter. So the top right hand corner is an image. It's a black and white sensor, and all we're looking at is a very, very tiny sliver of the light in and around 808 nanometers. So we're at the top, kind of at the top of the red edge, right at the NR plateau, very, very, this is like, okay, if I get a white pixel here, white pixel means a lot of light, black pixel means low light. So white pixel in this means healthy vegetation, means I'm getting a lot of reflective light off those orange tree leaves. And a black pixel like the asphalt road means, oh, we're not getting a lot of NIR light off something like that. The picture on the bottom here is from a FLIR Pro. It's a long-wave thermal camera. And you're getting, again, white pixel means, oh, hey, there's a lot of reflectivity here, which associates to health. And then the soil underneath is not emitting, again, emitting that light. The ground doesn't really emit light, hopefully, radioaction maybe. So that's the difference between these two. And again, the 808 nanometer one is a narrowband. We're seeing a very narrow sliver of light. And the thermal camera is what I consider a broadband. It's seeing a large expanse of information, and it doesn't see a very, very narrow thing. This is a crop from the previous photos. This is simply to show the difference in resolution. So we were talking about sensors, and pixels, and resolution. For thermal, if all you need to see is a blurry person in a field, you don't really care about knowing if they are male or female, or you don't know if they're wearing a red shirt or blue shirt, or if it's during the day. At nighttime, of course, you can't see that. But the resolution is also something to consider here. Now, in the multispectral world, the 1.2 megapixel sensor, this is the most popular sensor used. All of our competition uses this. SignRange, who has a booth outside, same thing. They have these same mono sensors. So the 1.2 megapixel compared to a 0.3 megapixel. So the 640 by 480, which cost me, I think, $3,000 from the thermal camera, is a quarter of the resolution from the exact same height. So this is just simply showing the difference between that. And as you can see, you've got a giant white blurry blob here, and you've actually got some more definition, contrast within the vegetation, even just looking at this one particular narrow band of 808 nanometers. So again, I'm sure you've seen these images before. These are just examples of thermal imagery, the usefulness of using a thermal camera for surveillance. Basically, again, reflected versus emitted. You got a power station, you got some lights around it, but you can't see somebody sneaking up on it if there's no light illuminating them, because the light illuminating them is basically the light source. It has to bounce off that person for the camera to see it. Whereas with a thermal camera, it doesn't care. If it's a person, they have a heat signature and they're emitting light, and then the thermal camera can see it. Same thing for the foliage plant situation here. You can't see the person and the plant's there. Oh, hey. Okay. So the difference between reflected light and emitted light, thinking about where the light's coming from, and the particular sensor and its own sensitivity. So you probably know about RGB sensors as a name. I'm going to briefly describe what an RGB sensor is. So an RGB sensor, a color sensor, like all your cell phone cameras have, is essentially a monochrome. It's a black and white sensor. And what they've done, and this is, again, the sensitivity curve, what a black and white sensor that's in your phone sees 400 to 1100. So what they do to a black and white sensor is they put what's called a Bayer filter. It's basically a 4-quadrant, a filter of 4 different filters over every single pixel. So this is something that's applied to the sensor manufacturing. You can see people on the internet scraping these things off like digital SLRs. Max is famous for doing this over the last few decades for people that want to see infrared light. Because if you think about it, we're only able to see blue, green, and red for the most part. So if you want to see pure infrared photography, you've had to do modifications to your camera to get that. But essentially what happens is each pixel has 4 filters over it. And one is blue, one is red, and 2 is green. So the green channel on your camera is what your camera is more sensitive to. You got a blue channel, a green channel, and a red channel. If you're looking at the same exact subject, the green channel is almost always twice as intense as either the blue on its own or the red on its own. And this is why. So you're essentially using a black and white sensor, and the sensor is able to separate the light with this Bayer pattern and create 3 channels from a typically 1-channel camera system. And this is what the spectral graph of an example of an RGB sensor would look like. So again, we've got that wavelength spectrum there, and again, the percentage of light that the camera is capturing. The blue peak is where the blue channel is, green, red, red, but you can see there's overlap. Even though you are capturing information in the red channel, you're also getting information that would be normally in all of those wavelengths. Look at the red channel's sensitivity curve. So if you were just using a Bayer sensor, you would get the entire spectrum of light here. And the red channel would capture information that would technically be in the green spectrum. And so RGB sensors on their own are useful, but not that useful for multispectral capturing. I'll get to that here in a minute. About what we've done in the last couple of years to try to use them to be useful. Thinking about broadband versus narrowband. Broadband, again, think of mono sensor, black and white. You don't get much information out of it. You see black and you say, okay, there's not much information there. You see white and there's a lot of information I just captured there. Thermal sensors. A white object is more information, black is less. If I say, what color is this bird? You don't know. You're looking at black and white photography. And so this is a great example of broadband. If a black and white image is broadband, you're not able to say, okay, this is red, green, blue, or a portion between the two to create yellow, purple, whatever. But if you're using an RGB image camera, you would be able to determine whether you are seeing separate colors. So this is the difference between a broadband sensor, which sees simply contrast over a broad spectrum of wavelengths, versus a narrowband sensor, similar to, say, an RGB. So broad would be like black and white, broad would be a thermal. Again, really large sensitivity. What you're doing on an RGB sensor is instead of seeing 400 to 1100, like we were looking at on that Bayer curve, the red, green, blue curve, there's a filter inside there called an IR cut filter. And that IR cut filter is essentially cutting out the IR light. So if you remember, the sensitivity of a typical RGB mono sensor is 400 to 1100. If you remember, the RGB curve went out past 700. Well, we don't want that information. Infrared light is really bad. If you were to take your phone and try to capture outside a picture with all the IR light from the sun, it would just be the most muddled, create, very dull-looking, colors would be muted. It's all that infrared light would overload the sensor. You wouldn't be able to capture the vibrant color that you would. So this is why we use IR cut filters in digital SLRs, Micro Four Thirds, larger format cameras. It's typically a piece of glass that's either placed over the sensor or placed on the back or inside of the lens. On some of the other cameras, it's just glued to the back of the lens. The Phantom 4 Pro, it's glued right over the sensor. We take that off and put some filters on there, which is fun. But yeah, so basically you're seeing red, green, and blue, and it cuts it off. It's an IR cut. So essentially it's letting all this light in and says, nope, nothing else past that. And so this is how you get pure or RGB color from a sensor that can see far beyond the end of red light. And getting back to narrowband, when you're using a mono sensor and you want to be able to see, again, like at 808 nanometer, you want to see a very, very, very small sliver of light, you need to use a narrowband filter. So for instance, this is our camera systems. At launch, these are the 15 filters that we're offering for narrowband filters. So you're getting back to being able to tell the difference between species. So if you said, okay, I need to be able to detect the contrast between, say, 615 and 590 or 615 and 518 nanometers, then you would buy those particular filters, install them into the camera, and then you'd be able to capture that narrowband with that narrowband, do your pixel map and GIS software, and boom, get your resulting image. So having a system that is adaptable and provides calibration and to support that is something is driving our own product line. And so these kind of narrowbands, the ability to design a system based on your particular use case, has been something that's really lacking, and we're trying to do a lot with that. So, like I said earlier, we've also been, in the last couple of years, we've been exploring useful ways to use RGB sensors, and this started with GoPros and DJI Phantom 3s, a lot of our customers wanted to do NDVI, with these RGB cameras because they're so affordable, relatively speaking. If I can get an NDVI image from a $400 camera, $500 camera, that is a lot different than paying for a 2 monoband camera, which doesn't, well, Technicolor has some stuff. There are some companies that sell like a single mono camera, but the prices would be thousands of dollars instead of hundreds of dollars. And so what we've tried to do is for the customers that are not looking for like the most pure, unadulterated pixel information, they just want like good information to start with so they can get an idea of what they're looking at. RGB sensors have been a very powerful tool, and so what we've been doing is we've been coming up with dual band, triple band filters to go over RGB sensors to force the light into particular channels and to try to reduce the crosstalk that you're seeing between these. So for instance, one of the ones that we're launching this summer is our triple band RGN. And so what this filter does is it captures a green peak, a red peak, and then an NIR peak. And so the NIR peak, if you remember from this graph, that 850 peak is unfortunately going to have all of the channels in it. So I'll get to reflectance calibration here in a minute, but essentially we're capturing as pure green and as red as possible with those real steep transmission curves. The NIR light is going to go into each of the 3 channels, but because we don't have a blue channel, the blue channel is going to actually store more of the infrared light than any of the other channels. So we can do NDVI, which is NIR and red. We can basically look at the red channel of the camera and the blue channel of the camera, do some pixel math, and boom, there we go, NDVI image. So we also have a triple band NGE. A lot of our customers are sad that the Sequoia doesn't have a blue channel. So sometimes you want to have a customer want the blue channel and a green channel and NIR. So there's other filter options for that. So this is a NIR green and blue one. So instead of the red channel having information, now the NIR light is going into the red channel. So just different options for the triple bands. So speaking about NDVI, what is NDVI? Well, it's an index. And an index is essentially, it's a way of capturing pixel information and converting it into reflectance percentage. And it's basically pixel math. We are trying to say that when I take a photo of something, that the value of the pixel relates to something in real life. And what that relates to is reflectance. It's how much light did that pixel capture, and what does that mean about that reflectance percentage? And we take the pixel number, so for instance on a normal JPEG, pixel ranges from 0 to 255. So the pixel value has a value. And we can take that pixel value and we can plug it into an equation and get a resulting integer value. And that resulting value becomes the value out of an index. So for NDVI, it ranges from -1 to 1. So depending on the particular value you get out of NDVI, that tells you something about the subject material that you've captured. So the triple band filter that we were just talking about has the capability of measuring NDVI, which is a commonly known as like a general health index. It tells you general health of a vegetation, and the GNDVI is used for just telling you how green something is. So that can be an example of species delineation as well. If one plant species is greener than the other, then you don't even need a nice mono sensor. You could just use something like this. So different use cases. And again, it all comes down to choosing the bands you want and basically creating the particular index that you're looking for. Most of these all say NIR, red, blue. They're very general terms. Most indexes beyond these more general ones go into where they're looking at the exact wavelength of, say, all these wavelengths. So they'll say, okay, we need this very specific 725 red edge filter, and we're gonna use that one with the 650. And so instead of red and red, or red and red edge, it's getting very specific in terms of the spectral band, and that gets into the spectral signature of the subject matter you're looking at. So this is beyond just general plant health and green and that kind of stuff, but you can get really into looking at different species and looking into moisture and pest control and lots of other information that the industry is still trying to catalog and make plain and easy for
So
to understand.
put it in dumb down way,
it's
down to filter, down to a filter that
It's
help.
Yeah, filtering the light to look at only the thing you want to look at, and then producing contrast, which is here, to get information from that particular wavelength. So what you're really looking for is contrast. We were talking about broadband, we were talking about white to black, and that is a contrast. That is the difference between an extreme to another extreme, a 0 to a 1. And so CIR imagery, colored infrared imagery, is a very common way to, from decades ago and still today, to display infrared photography from satellite imagery. And this is a very similar color scheme that they would use. They would say, okay, I want to put my plants in the red channel. The infrared light will go in the red channel of my RGB image. And so everything red is plant. And everything not red is background, blue-green channel. And so this is a very common way of showing it. We can do the same thing like we do with the blue channel. So I was talking about before, we were doing in DVI, our IR light goes in the blue channel. So our vegetation, particularly in some of the stuff that we process, is blue, and then everything else is red. So just different ways of showing it, and the contrast between the two channels is really what you're looking for. So this is the dual band filter, which is what we've been using for a long time. You're going to capture your red light in your red channel, and your infrared light will typically go into all the other channels. So pixel values, again, 0 to 1, black and white image. You assign a color to those particular values to make the contrast more apparent. So instead of a pixel value just a gray of 0.3, you can call it red. And so you can tell health about it. Coloring the 0 to 1 image is a lot more informative because you can see the contrast a lot better in this image. Yeah, and then reflectance calibration is very important. If you don't calibrate your captured multispectral data, the pixel values that you're capturing will produce index values that have nothing to do with what you're looking at. For instance, if you're not calibrated, you might get a value of negative 0.01, which with the NDVI scale of healthy plants being 0.2 to 0.9 means nothing. Whereas if you calibrate it, you get the correct value. So there's reflectance targets on the ground and also stuff in the air that are used to basically do that calibration. I have a booth out there, so I think after the demos and stuff, if you guys have questions, you can pick my brain.